please take this because it's not in your packet. Please. That's a good idea. Oh no, this one is on me. Oh, okay. That one ain't. All right, let's learn, you guys. So Unit 7, you guys only have 2 extra sections, and I try to teach them both in the same day because, like I said earlier, they're both kind of easy, not super hard to understand. And then, well, I guess here's a preview. And then in Unit 8, you have 1 extra section, which is also like not super hard. And then you start your own like units, which are Unit 9, which is a little bit intense, and then Unit 10, which is for sure like the most intense unit. But you're getting there. You're almost done with the content. Unit 9 is really short as well. So once we're done with this and the extra unit, the extra section in Unit 8, then we have like 4 sections in Unit 9 and like 8 in Unit 10. So we'll be done with good time, like good time to review. And last year, I just like, even when we were done with the content, we just kept coming in for like specific BC review if you're trying to do that. We'll decide when the time gets closer. That'll be like closer to spring break. But anyway, right now, learning 7.3 and 7.6. 7.3 is this cool idea of Euler's. Oh, you guys are probably going to think that I'm saying it wrong, Euler's method. But his name is Euler, like like that's the closest pronunciation, because he was like from a German-speaking place. He might have been German straight up. That's how they say it. No, they probably say it like different, but you know, Euler is the closest. We can like it's the correct pronunciation. Anyway, Euler's method is this idea of the follow. So it's easy to explain with a picture. So watch this. You guys know this whole unit is about differential equations. So let's say you had this differential equation that was like, I don't know, hard to solve, hard stuff, and dy dx plus blah, blah, equals hard stuff to solve. Okay. One way you've dealt of dealing with hard differential equations is with float fields. That way you don't have to get the solution. You can just make a little picture of what the solution would look like. Another way is the following. So let's say that you were just interested in specific points of this differential equation for whatever reason. Then what you could do is approximate the points using tangent lines. So here's the visual explanation. This is hard to solve, this equation that I'm circling right now. But what I could do is the following. I wouldn't know this as I'm solving this, but let's say the actual solution to this, which again, I would not know. Let's say it looks something like this. Ooh, something like that. This is why. It's the solution to that green hard equation. And obviously I don't know it. I don't know what that looks like in real life, but it's helpful for explaining what you're about to do. Okay. If you know already for whatever reason, like some initial condition that you want the thing to pass through. So like, let's say you know that this point is whatever, I'm just gonna make something up. Let's say this point is 1, 1. Then what Euler's method does is it takes, more motivation. Let's say this point is 1, 1, and you're interested in the solution. Let's say you're interested in f of 7 or something. Then I want this point way over here, f of 7. What is that point? What you can do is use the tangent line approximation that you guys know and love from unit whatever, where you take a tangent line But the thing is that method, if I tried to make a tangent line here, not my best. But okay, take that tangent line, then you can see the tangent line is way far off from the actual function value. But what Euler must have thought of, if he really did come up with this, sometimes people steal like other people's ideas and that. But what Euler came up with is that what if I did this? Watch this. Take the tangent line, since I know the dy dx and I know a point. That's all you need to make a tangent line. Take the tangent line at 1 and approximate this point close by. Like instead of getting this green point on the blue function, or like actually let me make that blue. Instead of getting that blue point, I can get this green point here. So that's a pretty good approximation of that point, somewhere in between. And then from here, get another tangent line, use the same derivative, get a tangent line from this green point, whoop, and get this third point. So now I'm approximating this point instead of this blue point. And then get another tangent line approximation, and approximate it from this estimation point that you got earlier. And now from here you can approximate you can get this green point instead of that purple point. And so it's just many steps of tangent line approximations. That's what Euler's method is. Okay, is this reaching you? Am I explaining this good? Okay. Questions? Okay, all right. Well, the idea is to use the tangent line approximation like that you know and love, but do it many times in a row so that the points are close enough that the tangent line approximations are good instead of like being way far off, like this purple one. All right, that's what's coming up. Some teachers, like what Mr. Little used to do, like this is in your packet because Mr. Little used to teach it with this little table. But to me, it's like I said, like I'm bad at memorizing stuff. So in May, I'm probably not going to remember this table or how I get this or how I fill this out or whatever. But if you don't like doing the long method of finding a bunch of tangent lines, then I'm sure everybody on the internet could teach you how to use this little table, and it might be faster. But really, it's the same amount of work, I think. All right, watch this. Here's an example. It says, given the differential equation x minus 2, and given that y of 0 equals 5, find an approximation for 0.8 using Euler's method with 2 equal steps. So, okay, watch this. Well, first let me say that this is kind of a system to do any approximation on, because I get the antiderivative really easy of this. But still, it's good for practice. So it's saying I'm starting at 0. I'm interested in 0.8. And I want to get there in 2 steps. So you tell me how wide each step would be to get from 0 to 0.8. Okay, all right, thank you. Yes. All right. So if you didn't catch it before, what I'm going to do is I'm going to take a tangent line of 0, approximate 0.4. Then I'm going to take a tangent line of 0.4 and use it to approximate the point that I'm interested in. So here is us doing that tangent line, or let me say step 1. Step 1 would be tangent line at 0, like I said. Y minus y value equals slope times x minus x value. And like I said, I'm getting that at 0, 5, so 0, 5. Okay. And then let me make sure you're paying attention. How would I get the slope of this tangent line? What is it? Yeah. Wonderful. Yeah, this says derivative equals this, so slope equals that. So here's me plugging in the x value, and from that, most of the time you'll have like x's and y, so you plug in both of these. But in this case, we just have the x's, so slope will be dy dx equals 0 minus 2, which is negative 2. That's me showing all my work, but of course you could have done that in your head and put the negative 2 there. Cool, then like I said, you're using this guy to approximate the next step, so 0.4. So you've seen this enough, I think, that I can skip some steps and say that y of 0.4, let me just go with this, y is approximately equal to negative 2 0.4 minus 0 plus 5. And obviously feel free to not put this minus 0 or to do a lot of this in your head or whatever. But I'm just trying to show all my work. So that approximation would equal, what is that? Negative 0.8 plus 5. Which is 4.2, right? Okay, and then now keep track of what you just did. You just said that the approximation for the actual function passes to the point 0.4 comma 4.2. So here's a new point that you're treating like it is on the function. Okay, you're treating this like it is on the function, then getting a tangent line here, and then using that to approximate 0.8. So now step 2, luckily we were only asked for 2 steps. Step 2 is do the same thing, but now with this new tangent line. So y minus 4.2 equals slope times x minus 0.4. Okay, and then again, don't forget you get the slope with the derivative, so I'm about to take that x value, plug it into the derivative. Hey guy, here, take this because it's not in your packet. dy dx would be x value, so 0.4 minus 2, which is negative 1.6, that's the inverse slope. And now we use this to approximate 0.8. Here's me speeding up before you guys get bored. Y is approximately equal to negative 1.6 times 0.8 minus 0.4 plus 4.2. And if you were to calculate that, you would get 3.56. And that would be your final answer, because that was your approximation for y of 0.8. So maybe I should say final answer, just to be super clear, y of 0.8 is approximately 3.56. Did it. Question.
So we're able to do this, and it kind of feels like rule sum. So is there, can you like take the limit and get more and more separation?
Somebody asked that last year, and I was like, wow, that's genius. But
I feel like a, it's not like a, I don't even know what that would be. It's not like what you're calculating.
Yeah, that's the thing. I couldn't figure out how this could, and nor am I aware of anybody like actually looking into that. But yeah, theoretically, if you made these steps really, really, really tiny and kept doing it forever, then you could get exactly what the graph would look like. But that just seemed like I said, it seemed like too big of a thing. But you should think about it, I guess, or look into if anybody's doing it. But it seemed too big of a thing because this requires you to know what point you're interested in. Whereas if you, well, I guess you could get a section. Like if you know you're interested in 0.8, then you could keep taking smaller and smaller steps and get a better and better approximation. And then it's not that much.
But we'll also just
Not that big.
differential equation.
In this case, yeah, but sometimes we can't.
No, but is there other cases where you actually can't solve it?
Yeah, as far as I know, yes. Yeah, so that might be worth looking into. Nice, good question. All right, anyway, example dose. Same idea, but this is an example that you guys can't solve yet, and I would have to think back way in my archive of differential equation knowledge to see if I remember how to solve this, or much easier, just approximate using Euler's method. So it says, y equals 3 when x equals 2. Use Euler's method with 3 equal steps to approximate y when x is 3.5. Okay, so let me just make sure you guys are set up good before I let you try this. Notice that they gave me the x value of 2, and I'm interested in 3.5 and getting there in 3 steps. So how wide is each step? Yeah, 0.5 sounds right. So I'll go from 2 to 2.5, from 2.5 to 3, from 3 to 3.5. Those are my 3 steps. Here, perfect. Okay, so I think maybe you guys should try this. Make sure you got it. Know what goes in where, like what numbers go in there. There's like 3 minutes. These are very tedious. You guys try it and see if you get an answer. Oh, you might need a calculator, but you can do something. Dang, okay, come on, yeah, that was quick. I just thought about it. If you mess up on the first step, then that can really change your whole rest of your answer. So I'll put the first step up here when you want to check, just before you get too far into your process. You need it for before you do get it too. You can check that your first step is good. It doesn't work with the way you think of it, but basically, tangent line approximation is only working in numbers that are really close together. So using a tangent line of 2 to approximate 3.5 is a bad idea because those are so far apart. But what you can do instead is use 2 to approximate 2.5 and those are pretty close together. Then pretend that point that you got is actually on the curve to get a tangent line there to approximate the new. Yeah. Okay. All right, here should have been your first tangent line. Hopefully you checked that. Then your step two, let's call this with step one in purple. Step two in purple would be y minus, at this new point, 3.5 equals slope times x minus 2.5. Your slope, if you plugged it in, here's me showing my work, but I'll skip it for part three, just so we can get to the answer quicker. Should have been 1.5. And if you take this and you plug in your next step, so 3, and if I calculated this right, then you would get 4.25 for your next one. So your new point would be at 3, 4.25. Good so far? Okay. And then you use that point to get to your third step, which would be at, oh shoot, we gotta get going. We're not gonna, I don't think we'll get through 7.6. So maybe we'll do 7.6 next week, at some point one day or something. Yeah, let's do that, and then we can be done with this after that problem. This one, again, you plug in your thing, and you get y minus 4.25 equals slope times x minus 2.5. You get your slope from the derivative. You should have gotten 1.75. Yes. My slope right though? Yes. Okay. And then you do all the work, plug in the 3.5. Actually, maybe I could show that for reasons that I'll point out in a second. Okay, and then you get a final answer of 3.5 about equal to 5.125. I didn't see that many people's final answer, but hopefully you got that. Yes? All right. Cool. All right. One thing that you've noticed probably is how tedious this is, so that's why the little table could be good. But some shortcuts you could take is that look at in each step, this 2.5 minus 2 will be just 0.5. This will be 0.5, and that will be 0.5, which is like what the table is trying to shortcut your way through. But that could be something you could at least save yourself some time on, is instead of showing the step, you could know that this will always just be the size of your steps each time, if you're trying to do that. But to be honest, like, this is another thing that in May I might not remember what is my shortcut and what does that give me and all that stuff. That's why I don't like the table, and that's why I don't like taking the shortcut. So I actually have to calculate the tangent lines each time, but you can see how long that takes and how tedious it is. So it's up to you if you want to learn from shortcuts or not. All right, and then the last one is the same thing, just with a table, and now that we don't have to get through 7.6, we have a good amount of time to do it. 2 steps. Yeah, I think you guys can handle this one too. So here's the chance if you messed up the last one, see if you can get this one. This one might be easier than the other two. So here's 2 minutes, you only need 2 steps. Yeah, because you forgot to put this negative. When you added it, you have 2.0 right? I don't Don't get too far on this, sorry, but because this would have been a negative, so it gets smaller. Yeah, all right. I'll start writing my work up here. So you still have 30 seconds before that beeps. Okay, there's your two tangent lines in green and in purple. And then if I calculated all this right, which I think I did because other people were getting that same answer as me, then you should have gotten that f of 2.6 is about equal to 1.78. Nice. All right. Last year I was able to get through this in one day, this and 7.6. But this year, I remember now that we did that in the actual class. So we had a full hour instead of 45 minutes or whatever. Okay, so then let's do this. 7.6. I don't want to do it tomorrow because I have an algebra meeting, members, every Friday. So we'll do it Monday. Yeah, Monday's good. In fact, we could even, would you rather come in and do it Monday morning? Or do you want to do it because we only have like 5 minutes of 7.5? Do you want me to pull every CC person up and teach you like that in class?
That sounds like
In
chaos.
class. It was chaotic. That's what I did last year for a little while, and I was like, no, this doesn't work. That's why I started the morning session. But since it's such a small thing and we have the class time anyway, like I want to waste your time. Yeah, okay, more people are saying in class. So let's do it in class, and if it's loud, then it's loud. And we'll see how the video turns out, but at least everybody will get a chance to be in the same room learning the thing. All right, so then we'll do that. No morning session. No morning session. We'll do it in class Monday. All done.